Hello and welcome to this Energy Tech webinar, Condenser Performance Essential Monitoring Air-in Leakage Evaluation and Reporting. My name is Kathy Regan, editor of Energy Tech magazine. I'll be your moderator for this webinar. Our presenter today is Dr. Tim Harpster, Director of Engineering at Intech Incorporated, and Jason Reynolds from Intech will also be joining us. Dr. Harpster is experienced in the area of steam surface condensers. He has authored and contributed to over 70 technical papers and presentations for EPRI, ASME, private utility seminars, and other professional organizations. Dr. Harpster's experiences include condenser performance testing and reporting, design and implementation of condenser performance upgrades via design, retrofits, air in-leak related testing, and manufacturing of unique condenser-related instrumentation for the advancement of condenser technology. Our session today will last 2 hours, and we will be taking a break halfway through the session. So with that, I will turn things over to Dr. Harpster.
Thank you for the introduction, Kathy. Jason is one of our account managers. As Kathy mentioned, he's here with me. He's our primary contact for Energy Tech and other outlets. Colin is our condenser instrument product supervisor and condenser services engineer. If you ever need technical assistance, interpreting data, or have general condenser questions, you'll probably be directed to him. And both will help me moderate this webinar. So I want to thank you all for making arrangements and setting aside time to join us on this webinar. And I also wanted you to know that the materials that I'll be presenting over the next 2 days are borrowed from a 2-day workshop that our company has been hosting for nearly 2 decades. Our company is very active in the heat exchanger research community. We are frequent contributors to EPRI, ASME, and other technical publications and conferences, so you may see us at some of those events. Our CEO, Joseph Harpster, served as the research and education chairman on the ASME heat exchanger subcommittee from 2009 to 2015. I put on the slide some of the comments from past attendees. You can see comments include phrases such as new information, excellent insight, and save several days of troubleshooting on this slide. And our goal at this workshop is to provide you with the knowledge to confidently troubleshoot condenser and to understand what tools are available to help you become a more efficient condenser system owner. Our best rated section from the workshop is our case studies. Unfortunately, that's tomorrow. That's tomorrow's topic. But our case study session has a pop quiz format. We start by teaching some troubleshooting techniques, and then we show data graphs from real operating utilities and ask what's the problem. So you'll be asked for your participation tomorrow, certainly. We have a team of people that put a lot of effort into keeping this workshop up to date and continually incorporate attendee feedback. So I encourage you to either send us a chat or an email during the presentation, and I'll do my best to address your comments with Jason's help. And so in summary, number one, we believe these materials are a complete, concise reference for your performance assessment needs. And we welcome your feedback. So if you feel something's missing or we can improve in some way, then please let us know. So this presentation is titled Condenser Performance Essentials. Over the next 2 days, I'm going to present information to answer the questions that are essential to maintaining a shell and tube steam surface condenser's performance. The first session will answer these first 3 bullets. Why do we care about the condenser's performance? What information and resources are needed to monitor performance, and how performance should be measured and valued, including common mistakes and difficulties. I think that you may find interesting. So some common mistakes and difficulties from others in your own expertise areas and positions. So this will be a review for some of you that have been condenser system owners for years, but for those of you that are new system owners, this will be the information that will be essential for all your performance analysis efforts. So I'll close today with some spectacular data that will prepare you for tomorrow's case studies. And like I said, the second session that will be presented tomorrow is the one that will receive the best comments on. So If you find that today's session is too basic, I promise you that you will see information that you haven't seen before, and it will show how others in your position have used data to solve problems, and show you how state-of-the-art condenser measurement technology and condenser upgrades can be performed. So with that, let's get started. On this slide is a diagram of the typical steam power plant. And you can see three major components of the steam cycle. You can see the boiler here. You can see the turbine here, and you can see the heat exchangers. And I want to share a story with you that highlights why we see our work as being valuable to the industry. In 2008, I attended an EPRI heat rate improvement conference. The conference is separated into three sessions, a day on boilers, a day on turbines, and the third day on heat exchangers. And much of the first day was spent talking about the boiler combustion and performance. You know, it's a large piece of equipment relying on many supporting systems. There's a lot of cool engineering problems to tackle when they involve operating and maintaining a 15-story fireball. So I can understand why an engineer would get some satisfaction, you know, developing skill in this area. Some of the second day was dedicated to turbines and turbine dense pack upgrades, turbine maintenance. And the turbine is a very expensive piece of equipment with very precisely engineered and manufactured parts. And, you know, again, there are some very interesting engineering problems ensuring reliable and efficient operation of this very expensive piece of equipment. And again, I can understand why an engineer would get some satisfaction developing skill in this area. But at the end of that second day at that conference, the turbine session, they had a roundtable discussion. And during the roundtable, participants were asked and invited to approach a microphone and ask questions of the panelists. And a young lady engineer came up to the mic and asked a question. She said, "I'm a new engineer. I'm trying to make some contribution to improving heat rate in my plant, and I don't know where to start. What advice can you give me?" And Joe Milton was one of the panelists, and he was a senior thermal performance engineer with RRI back then, and he answered with 3 words, but they were the same word, and he repeated it 3 times. He said, "Condenser, condenser, condenser." Now, the condenser is by no means a cool piece of equipment. If you were showing somebody around a power plant, you would show them the turbines, the boiler, probably pass right by the condenser without even mentioning it. On the steam side, it's a rusty and difficult to navigate confined space, and on the water side, it's probably one of the most foul environments in the power plant. The guy in this picture, his name's Neil. He was in a water box getting prepared to install some equipment, and there was this crimson-colored mud covering the water box walls, and he told me that the mud was moving along on the wall. If you can imagine that. That's something like you would see out of an Indiana Jones movie. You know, the condenser may not be the most desirable place to spend your time, but it contributes to power generation efficiency in a big way. So let's take a look at how the condenser affects efficiency of the Rankine steam cycle. This chart is a Mollier diagram that shows the enthalpy or energy per pound in the water throughout the steam cycle versus the entropy or the energy that does not contribute to work. And it's really essential to understand this chart because it's the basis for developing algorithms to determine efficiency of power generation and ultimately valuing your effort to improve condenser performance. And it's a great tool to describe why we care about the condenser. So let's walk through the cycle where the water is at its lowest energy state, its lowest enthalpy, and that's at the bottom of the condenser in the hot well at a low temperature, you know, about 90 degrees Fahrenheit. 70 BTUs per pound is the enthalpy of that water, and we try and add energy to that water by going through the low pressure heaters, high pressure heaters, and boiler. We're adding energy to that water all the time and getting it up to a point where we're ready to. It's now change state. It's now no longer liquid. It's a vapor state, and we're going to use up some of that potential energy by expanding that gas through the turbine, converting that stored potential energy into kinetic energy and extracting work with the turbine. So, the enthalpy in that steam decreases as it's driven through that turbine, and we're extracting work through the turbine, creating electrical electricity. And then that steam in this two-cycle system for this simple Rankine cycle diagram, we're going to put that steam back through the boiler through a reheat steam, and then drive that steam through this through an LP turbine. And so the amount of energy that is available to do work on the turbine is the difference between this high energy state after the reheat and the discharge state of the steam as it leaves the turbine and enters the condenser. And so that condenser, the condenser pressure determines the state of the gases leaving that turbine. And so if we can lower that enthalpy, lower the pressure of the condenser, it leaves more available energy to the turbine to create work and then turn the turbine and create electrical energy. And so keeping that condenser pressure low is a focus to increase the performance of electricity generation. So then that steam goes through a phase change that enters the condenser, goes through a phase change. We condense that steam down to liquid phase, and a lot of that energy is waste heat out the cooling water. And so then the steam returns to its liquid state at the bottom of the hot well. So that's how condenser pressure affects power generation. But then the natural question is, how significant is this effect? And so in this chart shows you that. In EPRI's Thermal Performance Engineer's Handbook, there is a table. Here's the reference here, and here's a copy of that table. And it shows thermal performance rules of thumb. And in this table are a few rules to value thermal performance improvements. I've highlighted the one that pertains to the condenser. And as we read it, it says for every 1/10 of an inch decrease in condenser pressure, we should see a 0.1 to 0.4% decrease in unit heat rate, or a 1 to 4 megawatt electric gain in a 1 gigawatt generating unit. So the way to use this rule of thumb is to calculate the difference between your measured condenser pressure and a calculated model or target condenser pressure. And you can see that every 1/10 of an inch over the target pressure is an increase of unit heat rate from 0.1 to 0.4%. Now this is a rather large range of effect on heat rate from a condenser pressure, and that will be a topic in a few slides from now, that range. But this is a great rule of thumb. It gives us a quick way to value condenser pressure reduction. But when you think about all the tasks you have in a day and prioritizing the most valuable use of your time, what may be more useful to know is how the condenser pressure typically ranks its impact on power generation efficiency in comparison to all the hundreds of systems in the power plant. And so in EPRI's heat rate improvement guidelines, they go on to rank controllable losses, typical controllable losses in the power industry. Here is the reference, this EPRI technical report. This list is ordered by the far right column, which is the impact to unit heat rate for typical deviations from the expected operation. And look at what tops the list. I've highlighted it, it's condenser pressure. And its typical impact, across the entire industry, the industry average, is equal to a heat rate deviation that is almost double the impact of the next highest controllable loss. And so this is why Joe Milton made his comment. This is why we view our work as valuable. And this is why he recommended that young engineer invest her time and resources on the condenser. And hopefully today you'll learn something new or be able to evaluate the condenser from a different perspective. Now I do have to acknowledge that the industry has put a higher priority on reliability when compared to efficiency. And all of these slides that I've shown have addressed efficiency. The way I choose to address this higher priority on reliability is this: higher condenser pressure is an early indicator for impending failure. There's few systems that are like that. So number one, that they're valuable to monitor and closely make efforts to continuously maintain, and two, prevent unforeseen events from taking a unit offline. So for example, several years ago, a customer of ours within Southern Company had an expansion joint failure that was located between the feed water pump turbine exhaust and the condenser. So they have, a turbine running a pump that's pumping the feed water into the boiler. And so that's steam driven, obviously. That steam exhausts into the condenser, and there's an expansion joint there. And that expansion joint failed. It allowed a bunch of air and leakage to come in at that joint. That failure let in about 100 SCFM into the condenser, which is a lot. But they kept the unit running, and they temporarily patched the joint while online and kept generating electricity. And the owners of the condenser at this plant, they placed a very high priority on keeping air and leakage low. If they had not kept it low prior to the event, then it's very likely that the air and leakage from the expansion joint would have tripped the turbine exhaust pressure limit and taken the plant offline. So in summary, and I think that's a very typical case. A lot of plants get themselves into a pickle because not monitoring or not having a continuous effort to address air and leakage or address fouling, and then when that event does happen, it causes real problems. And so again, in summary, giving a high priority to keeping the condenser pressure low is addressing both generation efficiency and generation reliability. That's the way I look at it. So this is, I'd like to get your feedback and hopefully allow you to share some of your experience with some of the other attendees in the class. The meeting console, as Kathy mentioned, has several ways to get your feedback to us. We might be able to enable audio so that you can ask a question. If you raise your hand, Jason may be able to unmute you. But otherwise, if you could type your answers into the question box. I have a couple of questions on the slide that I think would be helpful in the presentation for today, tomorrow, as well as give your peers that are also in the class kind of a frame of reference from where you're coming from. So if you could use the question box to submit your answers to these. The first question I have up here is, how do you value condenser pressure? So some possible answers might be, our value is consistent with the rules of thumb that I just talked about. The 1/10 of an inch is 0.1%, or maybe a dollar value per year, per month. You could also answer it, they're continuously monitored via a model and compared to a model target value. And so you get a value out like cleanliness factor or excess BTUs from the condensers. That may be a possible answer on how you value condenser pressure. Or if you're, a new system owner or a new engineer at the plant, maybe you don't know. That's okay too. But if you could answer that one. The second question deals with sort of why you're attending the class and what you're hoping to learn. Hopefully, if I can get your comments back on this one, I'll be able to address it specifically either in today or tomorrow's sessions. I'm asking what I'm asking is for you to describe the biggest event or ongoing issue that you've had with your condenser. So if it's, I don't know, air and leakage or fouling, or perhaps it's not related to those, maybe it's related to condensate chemistry. Maybe you're feeding a lot of hydrazine in, trying to combat dissolved oxygen. That may be an issue that we can address. Or maybe you have an upcoming retubing and you're looking for some options for upgrading. So your unit's up for retubing in the next couple years and you're looking for options. Anyway, those are all possible ways to answer the question. If you could answer those, Jason will keep an eye on them and interrupt me when appropriate. But I'll give about 15 seconds here and then we'll continue on with the presentation. Okay, so we've answered the first essential question, why should we care about the condenser? Now let's move on to what do we monitor? So I'm going to try and whip through this pretty quickly because you probably know most of this stuff, but there are some things that I commonly find are inconsistent with between me and some of the plant people. So I'd like to begin with condenser terminology. So condenser components that I refer to in a term that you may not be familiar with. So shown on this slide is a Westinghouse style condenser. You can tell it's a Westinghouse by this non-condensable offtake. That's the first term I want to talk about. So in the nuclear industry, you hear the word non-condensable a lot because entrained with the steam is reactor gas that is not air. It's hydrogen, oxygen, some radiolytic gases. And so they refer to it as non-condensables. So if I use that word and you are in the fossil industry, combined cycle, coal, whatever it may be, you're probably more used to hearing air. So air offtake or air removal section. But non-condensable and air are kind of synonymous when handling a lot of different issues. But like I said, the Westinghouse has a kind of an oddball design. The non-condensable air offtake is connected at the tube sheet. That's where the vacuum boundary is made. Most condensers have a pipe going through the transition region of the shell that connect into a shrouded region on the tube bundle, but the Westinghouse is a little bit of an oddball. That is not to be confused with the water box vent. That would be a vent on the cooling water side that allows you to ensure that the water boxes are filled. So sometimes I get that confusion when talking to other people. So see, the next term would be tube bundle. This is the bundle of tubes, the arrangement of tubes inside the shell, and inside that bundle there's what's called the air removal section, or you may hear it referred to as the air cooling zone or air cooler. And this is a subsection of tubes inside the condenser that are usually made of a thicker wall tube or different wall material, and it's where the non-condensables concentrate right before they get evacuated or pulled out of the condenser. And so that's called the air cooler or air removal section are the terms that I use the most. But that's referring to that subset of the tube bundle, those special section of tubes in the tube bundle. The last term is the duty. Really heat duty. The majority component of the heat duty to the condenser, or the heat load to the condenser, is the turbine exhaust, but other things like the boiler feed pump, turbine exhaust, drains, high temperature drains, those can all add to the thermal duty, the heat duty to the condenser. But the word duty is the thermal load on the condenser that gets transferred to the cooling water. So continuing on with some terminology, there are different configurations on the cooling system and turbine specifications. On this slide is the different condenser configuration envelopes. The arrows correspond to cooling water flow rate, and so here on the left, this left column is single pass water, so water that goes straight through a shell. And so there's single shells. You might have a small condenser like this on an auxiliary condenser with only one tube sheet, one inlet box and one outlet box. Or on maybe a large main condenser, you may have one large condenser with two water paths through it. Or you may even on a larger condenser have two independent shells with cooling water entering them. The next configuration is a two pass, where the cooling water enters one side, goes through a turnaround water box, and the warmer water goes back through the condenser. That's another configuration. You can have one shell, two shell, one path, two path, in that type of configuration. And then the last configuration is multiple pressure shells. And so you have two independent shells. They're isolated pressure-wise, so you can have two shells operating at two separate pressures with two LP turbines exhausting into them, and the cooling water would enter one, come out warm, and then enter the next one warm and come out even warmer on the high pressure shell. And so there's two shell configurations, there's three shell configurations, and there's even sort of integrated in series multi-pressure condensers like this. I'll show an example later on today about a condenser that's 2 zones with 70-foot long tubes that goes right through it. And there's different ways to handle the analysis for all of these, but it's the same basic principles that I'll be talking about today. So the last term I want to describe is the bundle arrangement. Very important term that maybe you don't know, but it's the condenser bundle arrangement. And at the heart of every condenser is the designer's bundle arrangement. If I can activate this movie, there we go, is the bundle arrangement. And so this defines the location of all the tubes, including the configuration of the air cooler or the air removal section tubes. It's the drill pattern for the tube sheet. It's the drill pattern for all the support plates in the condenser. This bundle arrangement plays a large role in efficiency and performance of the condenser because the patterns determine steam flow patterns, condensate management, and most importantly, the efficiency of air removal. So for example, in this bundle, you can see lanes, steam lanes. I'll show a couple of different designs with different lane configurations. You see the air cooler section, that's this central rectangular section of tubes right here. They're typically made from a different material, and it's shrouded. Typically, there would be a left baffle, a right baffle, a sloped left and right baffle here, and a top hood sealing it off. And then a pipe coming down this lane to draw off those non-condensables, that air, and take out to your vacuum equipment. So this is the air cooler. And this one doesn't have any condensate management, but some do, and we'll show some of that. But now, as part of my training to onboard me as an engineer here at Intech, I had to study all kinds of condenser files and reports. And as I studied all the reports and design sheets, it became apparent to me that there was a large variety in condenser tube bundle arrangements. You know, they don't all look like this. We've seen 2 already, the Westinghouse and this one. Very, very different bundle arrangements. And as I'm looking through all of these reports, it was as if no 2 bundles were the same. And the one thing that struck me as very strange is that it would seem that over time, some common features or best practices would work their way into the design. You know, perhaps a bundle pattern that condensed steam the best, the most efficiently, managed the condensate the best, manage the non-condensables the best would evolve over time, but that didn't seem to be the case. They just kept changing and quite drastically over time. And so it reminded me, as I was looking through them, it reminded me of flying machine designs from the early days of flight, where people built all these machines to attempt flight, but they didn't fly that well or didn't fly at all. And so I've assembled a few different bundle arrangements for you in the next couple slides for you to look at. And as I advance through these slides, I'll point out some of the unique features that affect the condenser's performance. And I'll show you some of the flying machines that I found amusing and similar looking to the bundle arrangements. So let's take a look at the first one. So this is this bundle over here is an Ingersoll Rand condenser, original design. You would see designs similar to these coming out of SPX, both their Ecolair and Yuba lines. But you know, a common feature is this shrouded, very tightly shrouded air removal section. You see these sections right here, very, very short lanes, by the way. Very, very short lanes on the periphery of the bundle. And then they have this lane and this lane here that they've made room for condensate management trays. So in here, there would be a horizontal plate that catches the falling condensate and drains it out to the side. And so that's done for 2 reasons. In an attempt to remove the condensate loading off of these tubes so they condense steam more efficiently, as well as pulling the condensate off into this low partial pressure, high temperature steam area where the condensate can be de-aerated, that the dissolved gases can come out. And so that's the 2 reasons for the condensate management there. Here's another design. This is the Westinghouse design. You would see designs similar to this coming out of Siemens and Mitsubishi nowadays. A very popular design. Westinghouse was very good at selling a lot of these. Some unique features are there is no shrouded air removal section here. It removes gases by a central pipe that conveys the gases down to the cold end. Some common features from these designs are these very deep, wide area steam lanes to allow steam to penetrate. This design, I'll point out that I'll talk about this design quite a bit later on, but this design did not work very well due to air management issues, as well as some tube vibration issues, but that's a separate topic. This is a Foster Wheeler design. So, you know, just a kind of a different variation of that first Ingersoll Rand tightly shrouded air cooler zone, but now this very large channel to convey the non-condensable gases up. You can see very tightly dense pack of tube bundle that's quite a distance from the air removal section. This particular condenser had, the reason I have it here is it had a condensate tray underneath it and was marketed as a de-aerating condenser because of this tray down here. It caught all the condensate, allowed steam to scrub that condensate to warm it up, drive off the dissolved gases that were coming out of this bundle design. That's an interesting design there. Here's another Foster Wheeler. I included these two Foster Wheelers because to show you how different they are. And these are just two of this particular manufacturer's designs, but very different. You know, no central air cooler. This one, there is a mirrored bundle facing off to the right here from this one. So there's no steam penetrating this wall. All the steam comes in from the top, left, and bottom here. And this is the air cooler section for this bundle. It's shrouded vertically and at a slope here. And you can see this lane for conveying the non-condensables over into the air cooler section. This one has particular problems with air binding in it as well. So moving along. This is another design. Very different from what we've seen before. 1985 this was installed. Very, very high aspect ratio, very tall, not very wide. The air cooler section is down here. This is shrouded here. You can see these very, very long and large areas that are not tubed that were intended to convey the non-condensables all the way down here into this air cooler. This one has particular issues with it as well. This is a Southwestern Engineering design. You would see designs similar to this coming out of TEI. You know, this shrouded region that you should have seen before. I showed this one because you can see here that the bundle is in two halves, an upper half and the lower half. This is done for two reasons. Either one, to reduce the cost of the tube sheets by having a smaller piece of metal to drill into, or to have a two-pass, one of those two-pass condensers where the cooling water would be entering this top bundle where the air cooler is, coming out hot and then entering the bottom cold. So this division is where the water box division is would be. And that's why there's an upper half and a lower half for this one. But anyway, you would see something similar to this coming out of TEI nowadays. Here's another TEI type design, sort of similar, but not split into an upper half and a lower half. Again, here's the air cooler section with an air offtake pipe going out the condenser that way. And yet another Southwestern or TEI design with the split half and the air cooler and some deep lanes. And so I've included on this slide, you know, kind of an array of different ones. You know, this is another Southwestern Engineering one. This is another Ingersoll Rand. Here's another Westinghouse, but very, very different from bundle to bundle, all with their own unique performance and performance characteristics.
Tim?
Yeah.
Before we move on, we did get a question on why the tube walls tend to be thicker in the air removal section.
Yeah.
They commented that the velocities they would expect to be the lowest in this section, so structurally you wouldn't think that thicker tube walls would be needed.
Yeah, so that's a good point. And so it's typically not for velocity. There is a phenomenon called ammonia grooving. So condensers that were tubed with Admiralty brass tubes, a chemical reaction can occur with ammonia forming from hydrogen being added to the system, where ammonia gas dissolves into the condensate. And so the ammonia dissolves into the condensate in an area where there's a high partial pressure of non-condensables. And so that area is the air cooler section. And so in those designs, ammonia, the ammonia in the condensate would etch away the Admiralty brass tubes in a region right at the support plates where the tube is passing through the support plate, because that's where that gap between the OD of the tube and the ID of the tube support plate hole is where water would get trapped, and not just condensate water, but also condensate with dissolved ammonia in it. And so that stagnated water right there would react with the copper and the Admiralty brass tubes and etch away the tubes. And that's called ammonia grooving, where the tube wall is corroded and eroded away because of that chemical reaction. And so you would get different material spec'd into the design to tube that region with a stainless steel or copper nickel tube in those air removal sections. So yeah, it's not really velocity related or impingement related. That's why you would typically see different tube wall and materials on the periphery. It's for a different reason to have that in the air cooler section. Thanks, Jason. Okay, so that was a good place to stop and have that question. So thank you for that. That completes a review of the terms that I used to describe the condenser components. When I use words like air cooler or tube bundle arrangement or non-condensables, you now have a reference for those terms. So now I want to review heat transfer fundamentals as it applies to steam surface condensers. And having a strong understanding of heat transfer fundamentals will allow us to understand root cause and allow much more effective troubleshooting of condensers. So shown in the upper left is the cross section of a condenser, showing the steam entering the condenser here, steam duty entering the condenser, transferring its energy to the cooling water, giving up its latent heat of vaporization, and this energy transfer raises the temperature of the cooling water. You can see that by this gradiented arrow here. The cooling water comes in cold and leaves warm. And this warmer water, as we saw from the Mollier diagram, contains a huge amount of energy that was given to it in the boiler, but we couldn't use it to create work at the turbine. And so let's take a closer look at a generic thermal circuit. So that we can introduce the concept of a heat transfer coefficient. And so, this is a typical equation that you would see in a diagram that you would use to evaluate different insulations for your home. It's very simple, very basic thermal circuit. The heat transferred from point A to point B through different resistive layers, R1, R2, R out, is directly proportional to the temperature difference between point A and point B. And so that equation is shown here. Q, the heat transferred from point A to point B, is equal to 1 over the sum of R's, the R equivalent, times the temperature difference between A and B. And so, like I said, the heat transfer is directly proportional to the temperature difference between point A and B by 1 over R. Okay, so now I'm going to show you an illustration of the thermal impedances that exist on tubes in the condenser, with the goal of showing you from a heat transfer fundamentals point of view how condenser pressure increases in the condenser. Now, I know this is very basic, but understanding the temperatures and heat transfer layers lays a foundation for understanding root cause for real-life problems like tube scaling, condenser air binding, imbalances in air offtake flow rates. All very practical issues come from understanding this type of stuff. So, so this illustration depicts the cross section of a tube. This gray ring right here is the tube wall, or is the tube. Okay, and all the thermal impedances to heat transferring from the steam outside here to the cooling water inside here are shown in this diagram conceptually. And so a steam molecule traveling toward the OD of the tube wall first encounters RNC, or the non-condensable thermal impedance. Now, for the tubes around the periphery of the bundle, the thermal impedance of this layer is nothing. There's no concentration of air out there, but in the air cooler section, this dominates heat transfer. I mean, you can have zero heat transfer, no steam penetrating down to the tube because of the air concentration. And so those are the two extremes of the R value of this layer. And I'll show, by the way, this, I'm not just, I'll show measurements of this in real condensers to show you that steam can actually be shut off on given tubes. It's pretty amazing. Okay, so moving along, the steam travels through this partial pressure of air, or non-condensables, and then the next layer is a condensate layer, and so there's a thermal impedance of that condensate layer. This is dripping condensate. Again, the tubes on the periphery of the bundle has that water being stripped off, and so that R value is quite low. But where tubes have a high condensate load, then that can become a significant impedance to heat transfer. And then we've got the tube wall and its thermal impedance there. So that's RT. The next thermal impedance is R sub F, so that's the fouling. So this would be scaling on the ID of the tube. Now we're on the inside diameter of the tube. So this could be a biofilm, it could be scaling, it could be silt that's deposited. And so there's an impedance to heat transfer there. And then the last layer is a temperature gradient in the cooling water around the outside of the core, and so that has to be accounted for as well, that thermal impedance in the cooling water. And so that thermal impedance is affected by the flow rate and the flow velocity and tube diameter and things like that. And so so that heat transfer, that Q, is transferred from the steam to the water, and the cooling water profile from inlet to outlet is shown here on the left. So the cooling water comes in at a cold temperature here, leaves at a hot temperature there, T circ water out. This would be the temperature rise of the cooling water from inlet to outlet for a given tube. And the logarithmic mean temperature is shown here. There's an equation for that I'll show you in just a second. But that becomes the basis for plugging values into the basic thermal circuit equation, which is shown here. So before we had Q equals 1 over R times delta T. For the condenser, it's Q equals that 1 over R, become the equivalent of that is a heat transfer coefficient times the condensing surface area A. And then instead of delta T, since the cooling water temperature is changing as we flow from inlet to the outlet, is a delta TLM. And so this becomes the equation for the basic equation for doing a lot of thermal performance analysis. And so we can see here is if any one of these R values that I just described up here in this diagram, if any one of these R values increases, the U, the heat transfer coefficient, the equivalent heat transfer coefficient decreases. And so If the duty remains equal in the condenser, so the steam duty stays the same, we're saying that stays the same. If the condensing surface area, obviously we're not going to add tubes, that condensing surface area stays equal, stays the same. If the U decreases, the heat transfer coefficient decreases due to fouling, due to air binding, due to anything, then the delta T, the delta TLM must increase. The delta T must increase to condense that same amount of duty. And so in this term, in this delta TLM, is the temperature of the steam, which is correlated by the steam tables to condenser pressure. And so in order to condense this duty with a lower heat transfer object, you need a greater temperature difference between the steam and the cooling water. And so that is the reason why condenser pressure raises when you foul or when there's air binding or anything like that. You need a larger driving force to condense the same duty that's being delivered to the condenser. Okay, so far I've presented general condenser component terminology, heat transfer terminology, some basic formula. The next section provides fundamentals of instrumentation and calculating performance target values. Now I've cut this section down quite a bit from how I used to present it. I only have one slide because I've lumped a lot of the discussion of issues with instrumentation into a case study in a couple of slides. So you're probably, if you work with condensers, you're probably already familiar with a lot of these instrumentation nodes that you would need to monitor condensers. So we'll just quickly look at them. This diagram shows, it's used as a guide to show all of the instruments to monitor the inputs and outputs of the condenser. So over here are the inputs to the condenser. The inputs are heat duty, which comes in the form of turbine exhaust, steam returns, water drains. So the heat duty is an input. Another input is the cooling water inlet temperature, the cooling water flow rate. That's the inlet to the condenser. Air and leaks, so the amount of air and leakage going into the condenser is another input. And then the shell pressure, the state of the pressure inside the condenser. The outputs of the condenser are the hot well condensate, both flow rate, temperature. Those things need to be monitored. The cooling water outlet temperature is an outlet. And then the another outlet is the vent gas, so the not vent, the non-condensable offtake gas mixture, so the air removal section flow rates and your vacuum equipment capacity. So those are the inlets and the outlets. And so there's instrumentation to measure all of this, and we'll talk about those in a few slides. Hopefully you're already familiar with a lot of this stuff, but we'll handle it in more detail in the form of a case study in a few slides. So with all that being monitored, you can calculate target values, and so there's specific ways to do that. And so what you need here is that input information, some design information from the condenser, which is number of tubes, tube material, all that stuff. You need that information. You can plug that into certain models and then make determinations. So that's what this flow chart is about here. And so if we take a look and we expand this green side of that flow chart, you need duty as an input. Most plants get their duty from heat balance models. A lot of plants don't have that. And if you don't have it, there's two other ways to get it. It's a cooling water balance. So you can use the inlet temperature of the cooling water, the outlet temperature of the cooling water, and the cooling water flow rate to calculate a duty. Now, a lot of plants don't monitor cooling water flow rate. So the third method, and it's a pretty good method, is a heat input energy balance. And so you look at the heat input to the steam cycle and the electricity outputs, the energy outputs. You subtract the two, and you get the condenser duty. That's called the heat input method. If somebody wants me to go into that in more detail, I can. I don't actually have a slide on that, but it's very straightforward. But that's a decent way to get condenser duty if you don't have reliable methods for either of these these other methods here. So another input to the models is you need some cooling source information, the inlet temperature, the total flow rate, and hopefully an outlet temperature, but the outlet temperature is really only used to calculate duty. But you do need the inlet temperature and the cooling water flow rate to get some values out here. Design information, number of tubes, tube material, tube gauge, tube length, that's all needed to go into the model. And then, of course, one of the most important measurements is an accurate, reliable condenser pressure that goes into the model. So you put all that information into, there's two different models used in the industry. One dominates, and that's the HEI method. There's also a series resistance summation method that's detailed in ASME PTC 12.2. It's very useful for doing some detailed studies, but it's not really useful for continuous monitoring. So we'll talk about those here. Two reference methods, HEI, currently on the 11th edition of Standards for Steam Surface Condensers. You should have access to this book. There's a lot of good information in here, not only on performance equations and monitoring, but also on the standard requirements for building shell and tube condensers and vacuum equipment. There's a lot of really good information in this manual. But the model specifically, let's talk about the model that's in HEI that's used almost ubiquitously in the industry. And that is it's a heuristic equation. It's a heuristic method. The general equation was developed by a guy named Orrock in 1910 before a lot of important technology, heat transfer technology, was understood. And so this guy Orrock, he made a general equation that and plugged in measurements from operating condensers to fit to generate that equation. And so it has evolved over time. It has evolved well, maybe not 11 times, but it's evolved. As recently as the 9th edition, they changed some of the inputs to this equation, and significantly too in the 9th edition. But it's a very good model now. It works very well, and I hope to show that to you in a couple of slides. But this is the model that's typically used in the Pepsi models and models that you have in your facilities. The other one is an ASME resistance summation. Again, I said it's detailed in PTC 12.2. It's based on first principles. It's supported by laboratory data. It gives you higher heat transfer coefficients than the HEI method, and it's very useful for detailed studies. But it's a complex method, and it doesn't apply. You would not want to use this for monitoring your condenser. So I want to talk about the HEI method and give you the basis for the formulation. This is the basic equation that Orrock developed. The heat transfer coefficient, the U-HEI, is equal to a product of all of these coefficients and values. And so we'll go through one by one each of these. So the first one that I want to handle is the cleanliness factor. Now, there's two different cleanliness factors. A cleanliness factor that comes out of your data historian is the continuously monitored performance percent of the condenser. This F sub C in this equation is typically refers to the designer's margin for designing, for speccing your condenser. And so if you go to your condenser manual and you see a cleanliness factor of 85%, your condenser manufacturer put a 15% margin on the condenser based on whatever agreements were made at the time of purchase to oversize the condenser for your particular application. And so if you read this paragraph here it is right here. It says the heat transfer rates published by HEI values are overall tube bundle U values to be obtained by the condenser under actual operating conditions, not single tube U values. We just talked about that. Because these values take into account parameters other than basic heat transfer across the wall of a tube, they are not meant to be used by designers as specific individual U2 values. They have conducted tests. Here, this method includes an allotment for the steam side effects described above. So it is a responsibility. Let's see, where is it? Oh, here. These are the effects that I'm referring to. Heat transfer coefficient is, here. The design of steam surface condenser must consider the effects of non-condensable gases which are present in the condenser, pressure drop of the steam as it flows in and around the bundle and tube bundle, and inundation as condensate falls through the bundle. So this value, this U equation, all these values, take all of this into an account. There's a margin for all of this stuff. So the translation there that I'm trying to get to is that if your condenser isn't showing 100% through your monitored values 100% after cleaning, then something's wrong. Now, it may not be significant. 90% is still a great performing condenser. But that 10%, something's affecting that 10%. And so it's just important that when you look at those cleanliness factors that come out of your model, really the goal is 100%, but there's diminishing returns of recovering that. But a good operating condenser should be up in the 90s. So one of the other factors in this Oryx equation is U sub 1. It's this combination of parameters in the equation. That's a straight lookup from this plot. The factors that affect your values are the tube diameter, shown over here, and the velocity of the cooling water. And so you would use most condensers are designed for about a 7 foot per second flow rate. And so right here you would go off and pick this 650 base value for U1. The next value is F sub W. This is the plot for F sub W. It is a inlet water temperature correction factor. In the 9th edition, this curve was drastically different. It's been corrected and much better fits actual data in the field. This curve does. So you'd probably want to make sure your models are using the 10th edition or later curves for this parameter. I have found in a couple of plants that they're using old 9th edition lookup tables, and so when the cooling water runs really cold, their models are just are way off. Here's what the 8th edition looks like. So when that cooling water got below about 55 degrees, the model predictions were quite a bit off. The next value is F sub M. This is a tube material and gauge correction factor. It used to all be normalized to 18 gauge Admiralty tubes. This used to be a 1. It is now 0.998 through the different revisions, but this factor is based on your tube material and gauge correction. And so here on this slide, I'm not going to go through this, but you have it in case you ever want to refer to it. Here are example equations, how to use all this information, how to use measured data to arrive at a measured heat transfer coefficient for your condenser, and target pressures for the condenser.
So I think we're right about an hour.
Oh, okay.
So I don't know if we want to pause.
Let me get through 2 more slides and then we'll pause, okay? So cleanliness factors, so in my opinion, cleanliness factor is the best value to trend to monitor performance. There's issues with it. We'll talk about those in a couple of slides. But you need 3 of the 4 of these inputs to calculate cleanliness factor. I don't like calling it cleanliness factor. You'll hear me refer to it as a performance factor throughout the talk because it doesn't. This factor doesn't necessarily deal with how clean the tubes are. So that's the reason I don't like to use the word cleanliness factor. A lot of people use TTD, but it's not really a reliable benchmark for performance. You have to use this properly, you have to have a lookup table and compare the measured value to an achievable value, and it changes with inlet temperature, duty, and flow rate. And so, yes, you can use it as kind of a thermometer, I guess, of how well the condenser is doing. But to really know accurately the performance of the condenser, this is a really tough way to do it, using a TTD. And so, using all of that information that I just showed, there's ways to get a target pressure. And so you can create a plot like this, where you've got condenser pressure on the y-axis, cooling water inlet temperature on the x-axis, and you've got a design point or a target pressure right here, and this would be your measured operating data. And you can do subtraction between these values and find out what your excess condenser pressure is. Okay, so let's take a 10-minute break here, and we'll continue on.
Okay, we'll go ahead and meet back here at 10 minutes past the hour.
Okay, thank you.
Okay, welcome back, everyone. With that, we will get started again. Just a quick reminder, if you do have questions, go ahead and type them in the question box, and Jason will present them to Dr. Harpster to get them answered for you. So turn it back over to Dr. Harpster.
Okay, so we just went over some of the basic formula to calculate the heat transfer coefficient and target pressure for the operating conditions for the condenser. I didn't go over it very explicitly, but all the formulas right there on that page, and you can use it and figure that out. But once you have the target pressure, the next 3 slides that I have is trying to monetize or value that excess back pressure. And so I showed this slide earlier, the thermal performance rules of thumb, that every 1/10 of an inch is a decrease in heat rate of 0.1, or sorry, an increase every 1/10 of an inch decrease in condenser pressure is a 1/10 to 4/10 decrease in heat rate, or 1 to 4 megawatt gain. And so the excess pressure would be the opposite. This would be an increase in heat rate, decrease in megawatt gain. But so where do these values come from? They're good rules of thumb, but you know, where does these numbers come from? And they come off of a chart that you should have access to. It's called they're called turbine correction curves. They could be called the generation correction curve. It could be called the turbine condenser correction curve. But essentially, it comes in different forms, but essentially has the same information on this. On the y-axis is a percent change in heat rate. Sorry about the lousy copy. I have better ones. I don't know why I kept this one. But anyway, y-axis is the percent change in heat rate. There are other graphs that say percent change in megawatts, but that's the y-axis. On the x-axis is the exhaust pressure, which is your condenser pressure. And so you can see 1 inch, 1.5 to 2.53 inches here. And then these different lines on here are correspond to different duties. So you can't read it, but that says, I don't know, 1.3 million pounds per hour, and this is 3.5 million pounds per hour. And so the way to use this, oh, by the way, we do have somebody in the class that's looking to build these models, so this is very applicable to what he needs. You would go here and you would create a function, obviously, to do this. You wouldn't do this on paper, but you would create a function that interpolates all this data, and you would find the duty that the condenser is operating at. So in this particular case, 3-point-something million pounds per hour. And this would be the line that we're going to extract information from. So then you would put in the measured condenser pressure. So let's say our condenser is operating with this duty at 2.5 inches. And based on previous work using the models that we just talked about, you calculated that the condenser should be operating at 2 inches. you know, with the cooling water flow rate you've got, with the cold water temperatures you've got, you should be operating at 2 inches. You would mark that on the line here. And then the way to use this plot is to, there we go. Get this distance here, get that height there, and this is your change in percent heat rate. So that is the effect of this extra 1/2 of an inch on heat rate. So this 1/2 of an inch is almost 1 full percent in heat rate, change in heat rate. So this is the exact plot that you would use and that your Pepsi models use to get that to the value of the excess back pressure. And so valuing condenser performance, if you want to take a look at it from the way you operate the condenser changes how you value it. So if you're in turbine follow, the cost of excess back pressure is the cost of extra fuel, which is a lot. But if you're in turbine follow mode, meaning you're trying to hit a dispatch electrical generation, when that pressure is high, you're just spending more dollars in coal or natural gas or whatever it may be. So the cost, the value, is the excess fuel usage if you reduce condenser pressure down to your target value. Now, if you're in boiler follow, for example, nuclear unit, or if you're just running full bore, right? So you just put in as much fuel to the boiler as you can, generating as many megawatts as you can. Well, that is a different case, because excess back pressure means that you're not generating megawatts and selling megawatts that you could be. And so this is a much better, higher value proposition for going and solving excess back pressure problems. So calculating the lost megawatts is a problem, is a different value proposition. So instead of calculating the fuel savings, you're calculating the lost revenue from lost megawatts. Recovering D rate. So I see some of the comments that somebody's up at a unit where they're derating because of maybe some air and leakage issues, maybe some fouling issues, but they're derating. And so solving those condenser issues is essentially recovering lost megawatts there. So that's a very high value proposition to go and get some resources to solve those issues. If you have variable speed cooling water pumps, that's a unique value proposition there, because in the cold cooling water months, you can cut back on your cooling water flow rate and still generate the same amount of power, or pretty close to. And so saving that station power that's being used to run those pumps is a very high value proposition there. So if you have variable speed cooling water pumps, reducing condenser pressure is a very high value. A very low value is condensate subcooling. By shipping that by producing condensate that's subcooled below the saturation, the pressure of the condenser's saturation temperature, you lose a little bit there. It's not much, but it's a very small value. It can be quite large in some of the larger units, but that's another value proposition there. So every 5 degrees you are subcooled with the hot wall condensate. It's about a 0.05% heat rate impact. Okay, so that's kind of the fundamentals for valuing excess back pressure. I now want to I want to circle back, and I want to use a case study to talk about common performance analysis problems. So problems you are probably experiencing at your facilities. I see a lot of comments about troubleshooting air and leakage issues, troubleshooting fouling issues, building models that are useful for your plants. I see a couple different comments that way. And so you will probably encounter one or many of the problems I'm going to talk about right now. So here's a case. This is data from a customer. On this plot, we see the station calculated cleanliness factor. So they have a model running, and it's pumping out a performance value that the condenser is running at. So you can see here that gross megawatts is shown in black. The condenser cleanliness factor from their models is shown in yellow, and it's operating at 70% performance at 200 megawatts, and when they go up to 350, which is their maximum electrical generation, the condenser performance improves. It goes up to 100%. Well, that's great. So the customer we had, he's a great engineer. He's within Southern Company. This whole project that I'm talking about here was a joint partnership between EPRI Clean Air and Southern Company. And when this data came out, it was very early on in the project, and a whole bunch of the team got together and they said, how can this be happening? And is the condenser more efficient or less efficient, more efficient at higher loads than at lower loads? And so, I worked closely with these guys, and they had all kinds of theories that at lower loads, you're at lower pressures, you probably have more air binding, or the velocity, steam velocity is in the bundle is lower at the low loads, and so you get lower heat transfer coefficients. There's all kinds of theories as to why this was being observed. And one of the most important lessons that you'll get in practice you'll get out of the case studies here in this case study and tomorrow is that validating your data is the very first and most important part of your effort. Validating the input, the measurements to all your models, the inputs to your observations, validating those measurements is extremely important. And so it became a question of, is this real or not? So what I did is, I guess I'll just show you the end. What happened in the end is I found a lot of problems with the data. And once we corrected the measurements into that same exact model resulted with this performance factor, a fixed 80%. Okay, so I'm going to go through a couple of slides and show you what I found, show you what to look for, show you tricks on how to find it and how to fix them. And so let's take a look at that. So the very first thing we look at is condenser pressure. Okay, and so the requirements for all of the measurements that we're going to go through and validate here, the requirements there's a really nice concise list of requirements in the ASME guideline, Performance Test Codes 12.2. If you don't own a copy or have access to a copy of this document, you should get it. It's got great information about the requirements for your instrumentation, as well as some other good general troubleshooting flow charts that I'll also reference later on. But this is a great reference. Anyway, the requirements are that you should have absolute transducers, not differential, not manometers. You want an uncertainty of the instrument of less than plus or minus 0.02 inches. You want it located 2 or 3 feet above the uppermost tube. You want static pressure taps baskets. This is kind of less of an issue, and I'll talk about that why. But this is the most common measurement found to be in error or inadequate during our evaluations. And so let me show you what I found at this particular facility. Here is a plot of, on the y-axis, condenser pressure versus time for all these different measurements. So when you validate measurements, use what you have. Grab steam temperatures and all the steam pressures, turbine exhaust pressures, grab all the pressures you have access to and temperatures, and do a comparison just like this. So these three are their independent vacuum measurements. They have 3 independent pressure transducers monitoring condenser pressure. They're all very good quality instruments, but they are not installed properly. And so I'm going to point out these values on this graph because it's tough. I know this plot's very busy, so I'm going to point out these values. These are 3 independent measurements, all measuring the pressure on the same condenser, same space. Should all be at the same pressure. And so you see these 3 very good vacuum gauges at this pressure, and that pressure. Almost 3/10 of an inch spread at this particular point. That is way too much. Your condenser pressure does not vary more than a few hundredths of an inch across the shell. And so the reasons, so in this particular condenser, we also have some test grade instruments that we installed as part of the project. So we have these 2 right here, the CMS. This is the, that's our acronym for our monitoring system, but these are test grade temperature, independent temperature, and a separate pressure measurement on the steam in the condenser shell. And then the other good measurement that this plant has is the hot wall temperature. It turned out to be a very good temperature measurement. Anyway, if you compare the saturation pressure from this temperature measurement to these test grade measurements, we see this. So these green lines show you where all those are. They're right on top of one another. I mean, within hundredths of an inch. So my point here is that we've got 3 very good quality transmitters. Unfortunately, they were installed without basket tips, with static taps near high temperature drains. At least that is the supposition of why these values were so wide ranging and why this one changed so drastically over time. So you can have good gauges without being installed properly. And so here's some general information summarizing the instrument accuracy targets and common problems. If you have differential pressure transmitters, you got to get rid of them. They're just typically just not useful at all. You need an absolute pressure instrument. And this is an important plot here. This is the acceptable tap locations on a visual scale, 1 to 3 feet above the top of the tubes. These are acceptable tap locations. This is not acceptable. There are regions in here that are not acceptable if they are near high temperature drains. So it really is of value to either walk down the impulse lines or to look at a drawing to figure out what drains come in near those taps, because you really don't want it near any high velocity or high temperature drains. We have installed and in special cases recommended to keep costs low, instrumentation down in here. It works very well, but you have to pay attention to, again, these measurements being near drains. You can get a very good measurement for performance monitoring in these regions, but you do have to, there's a lot more things to take account of. There can be very high velocities along the wall. There's a lot of drains that come in the wall. For that reason, this can be adequate, but it's not recommended to make measurements here. This is what a basket tip looks like. The requirements for the basket tip are in PTC 12.2. The requirements for parallel plates are in PTC 9, I think. Pressure measurement. Oh no, I'm sorry, that's ASME's. Yeah, that's right. I think it's pressure measurement. There's guidelines for how to do a parallel plate. But honestly, if you can find an area that's not near drains, the lowest cost, very acceptable, very appropriate method is just to have a wall tap. You do need to be careful and follow guidelines for doing a proper wall tap, but it's a low-cost way to get the measurement, and it can be very, very adequate. I like the location above the water boxes because you can get into that 1 to 3 foot region above the bundles, and typically without building scaffolding to put that penetration in. Typically also above the water boxes there aren't drains, and so you have a low velocity area above the bundle, above the water boxes. Again, it all needs to be looked at and assessed, but that's a typical low cost, easy location to put a tap in. The second error that I found in this particular case study was temperatures. As part of this project, we installed nearly 100 temperature sensors in the cooling water system. And so we had a lot of data to go on. What I've got shown on this plot is temperature on the y-axis, time on the x-axis. The station's original equipment for their cooling water temperatures are called out here. There's the B outlet and the A inlet temp. They're nearly a degree off. That's a huge error. And this is of original station equipment on these two paths. And I know that they're wrong. I'll show you another method to tell how they're wrong, but I know that they're wrong in this particular case because I've got 55 other temperatures telling me what the true temperature is in the inlet and outlet temperature. Oh, I forgot to mention, this plot is when the condenser is not running. This is a great time to do a cooling water temperature validation, is when there's no load on the condenser, because your inlet temperatures and your outlet temperatures should all lie on top of one another. It's a great way to do some validation, is to go back and find a no load time when the cooling water is flowing and do this comparison. The ASME PTC recommendations on temperature is that the instruments have no more than plus or minus a tenth of a degree Fahrenheit. The outlet measurements should be made less than 1,000 diameters downstream so that you're not losing heat to the environment from the piping. And it should be in a location that's not stratified of no more than 0.2 degrees Fahrenheit. That's a difficult one. I'll show you what we recommend for positioning outlet temperatures. If you do want to put some test grade instruments in, I'll show you the techniques that we use to get very good outlets on outlet temperatures on a budget. So there's the importance of temperature. Temperature can be a tricky measurement to make, especially with these accuracy limits. You can't just go buy any old RTD and attach it to any old transmitter and expect to be within plus or minus 0.1 degree Fahrenheit. They need to be a matched pair. It needs to be calibrated. You can't just drop in. Even a Class A RTD is not going to get you. If you drop a Class A RTD into some old transmitter, you're not going to get this kind of accuracy. And so all that information's here. You can read it if you want, but it's kind of a difficult measurement to make. But you can only make it with a matched RTD transmitter and transducer that's been calibrated. This is the difficulty of measuring outlet temperature. I recommend, well, what we do is we do a very simple CFD model. We know what outlet stratification profiles are from some of the other works that I'll show you. I know it's a stretch at this point to kind of to understand how we get the boundary conditions for this, but recommend doing a circ water analysis to find the best accessible locations. You don't always have access to the piping 100 feet away from the water boxes. It goes underground. You don't have access to it. And so you got to pick regions where it's kind of close to the outlet water box where the water is still stratified. And I mean, these are real world problems. And so we recommend doing a cooling water analysis. You can find planes in this stratified area that will give you the best chance at getting temperatures within a few tenths of the true average. And so that's how we recommend doing it. The shortcut is to just pick the furthest downstream that you can possibly lay your hands on and put an array of outlet temperatures there. Personally, I like to do this analysis beforehand so I know how good or how bad it can be. This is how we would do it. And so you would, out of this analysis, you would pick locations around at a certain elevation of where to put taps for temperature measurement. Cooling water total flow. Now, we actually had cooling water flow measurements at that plant. There was nothing wrong with them. I do want to make a quick comment about this. It's hardly ever measured, but there's some really easy ways to measure it continuously online. A velocity traverse is a one-time measurement. This is probably one of the most common ways to get a measurement, but again, it's only a single point. You hire a consultant to do this, or maybe you can do it internally. Same with tracer dilution. They insert a dye, measure the dilution using a fluorometer, and get the flow rate that way. Again, that's a one-time test. Ultrasonic, you can, I've seen some very good success with ultrasonics, but I've also seen some pretty bad failures with ultrasonic flow measurements. It's a great technique, great use of the instrument. Getting a plus minus 3% accuracy to meet 12.2 is difficult, but maybe you don't need that. This is the method that I recommend. It can be done very inexpensively, but if you use a differential producer, which is essentially the water box restriction from the water box to the piping, that is enough in most cases to get a pressure difference that you can calibrate to flow rate. So you would install differential pressure measurements, hire somebody to do, or do your own velocity traverse or tracer dilution to calibrate those differential producers, and now you've got a permanent online cooling water flow measurement for years to come. And the cost of installing this instrumentation can be around the same cost as a one-time flow test velocity traverse or tracer dilution. This is a really nice way to get cooling water flow rate, and I'll show you some results on that in a couple slides and tomorrow as well. You can do an energy balance. That's can be quite tricky too, to get cooling water flow rate, but this would be something you would get out of your models. Anyway, that's that. So this is what a differential producer data would look like. The way we do it is we would recommend doing, again, a CFD, very simple model. Just set up the model, predict what pressures you will get at the operating flow rates. If you go down to one pump, you should model that to know what that pressure is going to be, to make sure that you have a range that's going to be acceptable for your flow monitoring requirements. But I would recommend just doing a solid model, setting up the flow rates at the different flow regions, the high flow, maybe the 2-pump operation and a 1-pump operation, getting those pressures, finding the optimal positions for the pressure taps to get the largest signal. Those are all efforts that I would recommend. It's very simple. It doesn't need to be very costly to do that. But then you have some engineering analysis behind your work instructions of where you're going to put your taps and spec your instrumentation. And so this is what the data looks like. There's cooling water flow rate here on the y-axis, differential pressure for this particular water box to pipe. You can get 25 inches at full flow between the water box and pipe for this particular application, which is more than enough to get a measurement of flow rate. Some cautions: it can be tricky to actually implement something that doesn't need maintenance over long term. I would recommend using a tap that can be isolated so that you can clean it out. You can disconnect the instrumentation, do whatever maintenance you want. Definitely recommend stainless steel fittings so they don't corrode and become obstructed over time. Eventually, it's tough to see this, but this is an unisolated valve that will corrode and be plugged over time. So this is not very useful, this particular installation. But again, recommend using stainless steel fittings and plan for either some way to manually purge those lines, or I would recommend automated flushing. You just have a system, just flush it on a daily basis or whatever. Keep that line clean and free of debris and corrosion products. Non-condensables and condensers. So there's a couple different ways to measure non-condensables and condensers. This particular case study, they have REAVAC instruments, which I know some of the attendees have, and we'll talk about REAVACs a lot more tomorrow, but some today. There's a couple different ways to measure non-condensables. There's only one way to measure the vacuum equipment capacity, and that is with a REAVAC tool. That's with something that's between the condenser and your vacuum equipment. That's how you're going to get your vacuum equipment flow rate. So there's only one way to get that measurement. But there's a couple different ways to get air and leakage. You can use a REAVAC measurement, or you can use discharge side measurements. Probably the most common one is a rotometer. It's a common choice. Excuse me. But that's not an online measurement. There are some electronic flow sensors that you can put on the discharge that measure the airflow. There can be issues with those, but that's another valid way to measure air and leakage from a condenser. I'm a big proponent of making this measurement on the suction side, because with one instrument, in the blink of an eye, you can determine if air and leakage is a problem. In one instant, one parameter, one measurement, you can, in the blink of an eye, you can figure out if your vacuum equipment is working properly. You can measure it continuously online. You can swap pumps or steam jets in and out and know the capacity is okay, or compare them to one another. So I'm a big proponent of measuring this on the suction side of the vacuum equipment. We'll talk about that later. This is the REAVAC instrument, which many of the attendees own. Again, this is a probe that gets installed through a ball valve assembly. It can be installed or extracted while online through a ball valve assembly and this sealed compression fitting gland there. But it goes in this piping. You can install one anywhere in this piping in the common or individual offtakes. There's some advantages that we'll talk about tomorrow, but this is the REAVAC instrument for monitoring vacuum equipment capacity and air and leakage. And these are some of the output parameters from the instrument: air and leakage, volumetric flow for pumps for measuring pump capacity, mass flow for measuring steam jet capacity. But the most important parameter is this water vapor to air mass ratio. This is the most important parameter from this instrument, and we'll talk about why in a few slides. So again, here's that case study with the wacky cleanliness factor that we have now corrected by validating our data. Now we know that there is no mysterious reason that performance is changing with load. It's actually quite steady. And so again, going back to the beginning, here's that customer with his models. A lot of people spending a lot of time to theorize why this is occurring, really wasting their efforts. And so, as I've shown, I found errors in their plant measurements. Anyway, if we just correct those inputs to the model, everything works out just great. And by doing this, here's what I want to say. Oh, I chose this case study for two reasons. Number one, always validate the data before troubleshooting. And number two, have faith in the formulas. The formulas are actually really good. The HEI formulas are really good for monitoring performance, even in changing conditions such as inlet temperature and load changes. They do work quite well. Here's another case. Here's a plant, a different plant that's monitoring cleanliness factor with their own models. And you can see it's widely varying and almost no correlation to changes in electrical generation, just kind of all over the place. And here again, this may be something you're seeing out of your own models, but if you correct the data going into these models, it's the same exact formula that I'm using to calculate these values, but with test grade instrumentation. Look, it can be really nice. Showing this condenser operating up around 90% pretty steadily. The next graph is what I found to go from this wild cleanliness factor calculation to this nice steady one. This particular plant had pressure issues. Wow, so here is their plant equipment measuring shell pressure, hot wall temperatures, hood exhaust pressures. You can see here 0.2 of an inch difference in the shell pressures. Two different measurements showing pressures that are 2 and 3/10 off from one another. Hot wall temperatures, look at this. The hot wall temperatures, look, they're great. If you calculate the saturation pressure from the hot wall temperature, it's almost right on top of the test grade instruments. So hot well temperature can be a great tool to validate your condenser shell pressure measurements. And then the exhausted temperature, kind of garbage, but it all goes into the comparison. Something else that I found at this plant was cooling water outlet temperature. Here again is a no load time period. The cooling water is flowing. There's no load to the condenser. And so you would expect the cooling water inlet and outlet temperatures to be right on top of one another. But you can see here it's all over the place. Here's one. The biggest one is 60 degrees Fahrenheit. The lowest one is at 56. Wow, it's a 4 degrees temperature spread across the station equipment. Whereas we had installed a whole bunch of RTDs for test grade instruments for inlet and outlet, and man, they're right on top of one another, all within a tenth here. So that's what led to the change between the red line and the blue line there. So this is a plot, or this is a table. This is a big summary of the last couple slides showing typical findings from our basic evaluations. I'm not going to go through it all, but it basically shows, what we typically find on condenser pressure, what we would typically recommend. Same with cooling water, air and leakage, exhauster capacity, all this stuff. So you can read through this, but it's a big summary of all the slides that I just showed. And this is what a package, if you were wanting to upgrade parts of it or all of it, this is what a package would look like. Temperature, pressure, a re-evac monitor, and cooling water flow monitor. Now, so far the information I've presented is pretty basic. I mean, that's the title of the class implies. It's the essentials for condenser monitoring. Tomorrow I'll show the case studies from plants that most have less instrumentation than what's shown here. Some have more, some have less. But the case studies will all be real problem-solving cases and not just the improvement of a calculated cleanliness, but actually, solving problems. I did want to have a transition here, section to transition us into those case studies tomorrow. So also as part of the title of the class, air and leakage is a particular focus for this class. So the next section will be the last section of today's presentation. We'll prepare you for the case studies tomorrow. I'm going to show you new ways to troubleshoot the condenser in having a clear visual understanding of how air affects the condenser has been, in our experience, a very effective teaching tool. Not only that, the information I'm about to show you, you won't find anywhere else in the world, and it's really cool. It's really cool stuff. So let's start off this next section is state-of-the-art air and leakage training. So in ASME PTC's 12.2 appendix guideline, they provide for how to measure air binding, or what air binding or air looks like inside the condenser. And to perform this test, when the unit's offline, you walk into the outlet water box and you fit a bunch of the tube ends with temperature sensors. So here in this guideline, here's the guideline, here's the image for these sensors. You walk into the outlet water box, you look at the tube sheet and you see all the tube ends sticking out. Now this tube end is a little bit exaggerated. They don't stick out that far. But this is the water box side of the tube sheet. This is the steam side of the tube sheet that you can't see from the water box. But you would go in and you would attach temperature sensors. And so in here they recommend type E thermocouples. We do quite a bit differently. But essentially you get this temperature measurement. And then when you leave, the idea here is that when the unit comes back up online, if the unit has air storage in it, air is a terrible conductor of heat, can greatly reduce the tube's ability to condense steam. So when the unit comes back online and water and steam are flowing, these temperature sensors measure temperature rises of the cooling water and then use Q equal m sub c or m dot c sub p delta T to calculate heat transfer. And where that heat transfer is low, or where that temperature rise is low, that's where you have air affecting the condenser. So this is how the standard for measuring air binding. And so we have some great results to show you in a couple of slides. So this graph is an attempt to illustrate the ideal case of cooling water temperature rise as steam is condensed. The left side is the inlet cooling water box. The out is the outlet cooling water box. And so you would expect, if all the tubes condense the same amount of steam, you would expect the cooling water to enter and rise uniformly across all the tubes. Now that's the ideal case, and that never happens. In every condenser, there are air pockets that form in some way, some large, some small. Some designs control it better than others. And so this is another illustration. Before I get to real life cases, here's another illustration showing how air gets concentrated in condensers. And this is a slide that I've used many times. It's the title of this slide is called Condenser Air and Leakage is Not a Problem. Now the title is meant to be provocative. It's meant to challenge the way you think about air affecting condensers. It doesn't matter if you have air leaking into the condenser. It's okay to have air leak into the condenser. The reason I say that condenser air leakage is not a problem is that if air can enter and exit without causing pockets of significant partial pressures, then the condenser performance isn't affected. The true cause for all the problems that people typically associate with air leakage is really air storage. And that's where air comes in and sets up a partial pressure in pockets here and shuts down condensation of these tubes. And that loss of condensing surface area is really what increases condenser pressure. It's like making your condenser smaller by shutting off these tubes. And so this air storage can occur in two different ways. The first way is called what we call a stagnant zone. All condensers have this type of stagnant zone. It's where air concentrates in the air cooler section, in and around it, and it forms there. And when air leakage is high, this bubble gets bigger. When air leakage is low, this bubble gets smaller. If the vacuum pump capacity is a problem, I don't know, the pumps have a leak or the pumps have a problem, then this air binding will increase. It has the same effect as a high air leakage. If you turn on a second exhauster, you may shrink that bubble. So stagnant zones form from high air leakage or poor pumping capacity. The other way that air is stored, and I'll show you real life examples of this, is air binding. It's different from stagnant zones. Air binding is configuration caused. Air collects away from the air removal section. So all those crazy designs of tube bundle arrangements that I showed you, some of them have areas where the air goes before it gets to the air cooler section. And it'll build up a pocket until it grows to a size where it reaches over and then that gas can be evacuated out of the air cooler section. And so these are design caused air storage, and that's called air bound zones. And so let's take a look at what some of these stagnant zones and air bound zones look like in real life. Okay. So we have, like I said, we have a service for special projects. They're really condenser upgrade projects where it's necessary to go in and measure the size of these airbound zones because there's considerable benefit to getting rid of them. So we install hundreds of temperature sensors. We use an approach, we use an instrument called a high density temperature array. The high density temperature array, unlike the device that I showed you in the performance test code, that's a single point measurement. And you have to run one wire for every one measurement you run. It's a real pain. We've done it before, but we've moved off of that. We now install these prefabricated devices. We sandblast the tube sheet, put down a base layer, and then attach these prefabricated high density temperature arrays. And so these prefabricated devices have temperatures sensors distributed all along it. So this 2 foot long device here has 40 temperature sensors along it. And so you can see here, here's a tube sheet that we are in the middle of instrumenting. You can still see some of our templates on there, but there's a high density temperature array. There's one, there's one, there's one, there's one, there's one. And so when the unit comes back online, we can see the temperature rise profile, which is shown here on the right. And so the color scale is shown here at the bottom. This is the temperature rise. So blue is 0 degrees temperature rise of the cooling water going from inlet to outlet. 21 degrees is 21 degrees temperature rise from the inlet to the outlet. So here on the periphery, you know, it's very high velocity steam. There's very little condensation out here. We have high heat transfer coefficients. We have 20 degrees temperature rise. But look at this dead zone in here. We've got a stagnant zone here in the air cooler section, a stagnant zone there in the air cooler section. This particular condenser, if you haven't guessed already, it has a solid baffle here, being the boundary of the left boundary of the air cooler section, and a solid baffle here and here. And then the gases draw off from a pipe that reaches in here this way. So this is the air cooler, 2 air coolers per bundle. This is a stagnant zone. This is an airbound zone, right? This is outside the air cooler. It's a region where air goes and dead ends. And so these tubes are all affected by air binding. So now another way to look at this this information. Oh, by the way, I didn't describe it, but here this outline shows the locations of all our temperature sensors that you saw in this stitched photograph over here. And you can see how this is not CFD that I've got here. This is just interpolation of real life measurements, giving you this profile. So this is a real profile. So anyway, I find it useful to use the condenser pressure and inlet temperature and flow rate to transform this through formula to not be a temperature profile, but to be what we call performance profiles. And so now the color scale represents not temperature, but the performance of the tube. And so you can see here that kind of a light red is about 100% of the HEI value. Yellow is about 75% of the HEI value. And then blue is junk. You know, it's less than 20% of the heat transfer that you should be getting. And so you can see here the effects of air binding in this particular condenser, affecting heat transfer all the way out to the periphery. Now this bundle is affected a little bit by, I think, high air and leakage at this particular case, or maybe scaling, I can't remember, but you can get a sense for where the air binding is with this profile. So now I want to show you another air binding profile. Yeah, this one here, this is a Westinghouse. This one's really cool. Okay, so we've got another way to do temperature measurements. We can actually measure temperatures inside the tubes. Now, we wouldn't recommend this for just somebody doing performance evaluations. This is a very specific need for this very specific project, that we wanted to have temperatures of the cooling water inside the tubes along these 75-foot long tubes. And so everywhere you see a black dot is where we have a temperature measurement. So there they are in the outlet, there they are in the inlet. So we've got hundreds of temperature measurements here measuring the temperature rise. This is what the thermal profile looks like for this condenser, for the upper and lower bundle. And so if we can change that into a performance profile, now you can see what the air binding looks like in the Westinghouse profile. I like to identify this yellow boundary, this 75%, that kind of gives you a nice bubble boundary for all the different zones. And you can see what these airbound zones look like for this particular condenser. I have one more case here, air storage. Actually, this is really too much information, but anyway, we got this smaller condenser, 90 megawatt condenser, we've instrumented the outlet water boxes. This one is animated. I've got an animation of this airbound zone, and that gives you it will give you an idea of how an airbound, a stagnant zone can grow into a very large stagnant zone. So here's the condenser on its side. We've got measurements all over this condenser. Here's me inside the water box with all the instrumentation on the tube sheets. And at this particular site, we wanted to do an air and leakage test, so we purposely introduced air and leakage. The air and leakage was at a very, very low value of 5 SCFM, and we purposely introduced an air and leakage all the way up to 60 SCFM and shut it off. And so I'm going to animate that performance profile over this time period from low to high air and leakage. So here is that bundle. It's actually got quite a bit of scaling in this bundle. The cleanliness factor only goes up to about 80-some%. But you can see here, low air and leakage, we have an airbound zone outside the air cooler here, that bubble right there, and we have one over here as well. And then as we animate the slide, we're going to increase the air and leakage. You can see how the high air and leakage just shuts off at a huge number of tubes as we go up to 60 SCFM. So now more than half the bundle, most 60% of the bundle, has less than 20% of the heat transfer coefficient that it could have because of that 60 SCFM air and leakage. I've got one last case study that is a really nice depiction of an airbound zone. This one's another oddball. Here's a bundle. This is the air cooler section in this one, so this is shrouded over here. You can very quickly see that this is an air-bound zone out here away from the air cooler. So this air has to travel down this section to get to the air cooler before it can be pumped out. And this one's kind of interesting because the air leakage stays really low on this unit. What happens is there's a condition that arises that decreases the pump capacity. So I wanted to show you how a stagnant zone can form, not from high air and leakage, but just because your pumps aren't performing or there's a leak at the pump. And so we're going to animate this, and you can see, you can probably already anticipate what's going to happen. This blue is going to grow as the pump capacity gets not shut off, but goes lower. And so now this airbound zone has grown and a stagnant zone has reached out and come over here. So now you have, hopefully now you have a picture in your head of how air envelops these bundles. And that's going to be really important to troubleshooting the condenser, especially air and leakage problems. So I'm going to show you how to use the reevac data, reevac that's installed in these air offtakes. I'm going to show you how you can use one parameter from that reevac and know for certain if it's affecting back pressure. You don't even need to look at any other data, just one value off this instrument. You'll know if it's affecting back pressure. And then you look at two other parameters and you'll know if it's high air and leakage or your pump capacity. And so that's the end of today's session. Again, I think you're all probably waiting for the case studies that I'll be presenting tomorrow. They're really good case studies that we highly rated. But hopefully now you have the fundamentals down pat, and we can get into a lot of troubleshooting tomorrow. There will be a handout that I'll need you to download tomorrow and have hopefully printed out or maybe on a second screen for your computer to look at the data plots as we go through and troubleshoot the data. So expect to download that handout tomorrow or print it out early so that we can get going on the case studies tomorrow. Kathy, I'll turn it over to you.
Okay, well, thank you everyone for joining us today. We did record today's webinar, and we'll send you a link tomorrow morning, maybe this afternoon if I get it done. You'll have access to that recording for 30 days if you'd like to review the session, and we will see everyone back here again tomorrow at the same time, noon Central Time, for another 2-hour session. Thanks for joining us today.